All right, let's get right into it. You ever stop and think about how your phone just knows your face? Or how a self-driving car can weave through a crazy busy street? Well, it all boils down to one thing: teaching machines how to see. And this isn't just some dry story about code. No, it's this incredible journey of discovery. Basically trying to copy the most amazing machine ever created, our own brain. And yeah, that's really the big question we're tackling here. How in the world do you teach a hunk of metal and silicon to, well, to see the world like we do, to get all the nuance and detail that our eyes just get instantly? I mean, that one single question is what's fueled decades of just mind-blowing innovation. So, to figure this out, we've got to go way back to the beginning. See, the whole point of AI originally wasn't just about building clever gadgets. The real dream was to understand ourselves, our own minds, by trying to build one from scratch. And that journey, oh man, it was a total roller coaster. You had this huge excitement in the 40s and 50s with the first artificial neuron and then the perceptron. People were thinking, this is it, but then, bam, the limitations hit and we plunged into what's known as the AI winter. All the funding dried up, everyone got super skeptical. It wasn't until the 80s when multi-layer perceptrons, or MLPs, showed up that things started to thaw out. And this quote here really nails the mindset back then. The whole idea was to make a kind of digital mirror. The researchers weren't trying to build our replacements, not at all. They were trying to understand the very process of learning by making a machine that could learn. And that idea, that inspiration from biology, it's the absolute key to everything we're going to talk about next. But even with all this new progress, these MLPs, they slammed right into a brick wall, a huge one. Because when it came to images, these networks were, for all intents and purposes, blind. They just could not cope with the insane complexity of visual data. So the problem was twofold, really. First, you had what they called an explosion of parameters. Just imagine trying to connect every single pixel in an image to every single neuron in the network. It was just computationally impossible. And second, these things had zero spatial awareness. They looked at a picture and just saw a long, jumbled list of numbers, completely missing the fact that, this pixel is next to that one. All the structure was just gone. And you can really see the difference right here. On the one hand, the old way, the MLP, it's a complete, tangled mess, just chaos. But on the other hand, the new idea, what would become a CNN, it's so much more elegant, it's structured, it's efficient. The neurons only look at a little piece of the image at a time. This, right here, was the massive shift in thinking that computer vision desperately needed. So where did this genius idea come from? Well, you can probably guess. We went right back to biology. The answer to machine vision was hiding in plain sight, in how we see. By studying the structure of our own visual cortex, researchers came up with the idea for convolutional neural networks, or as we all know them, CNNs. The magic of CNNs really boils down to two core ideas. First, something called local receptive fields. So instead of a neuron trying to look at the entire image at once, it just focuses on one tiny patch, kind of like how cells in our own eyes work. And second, this brilliant idea of weight sharing. This means you design one little pattern detector, let's say it's looking for a straight vertical line, and then you just reuse it, sliding it over the whole image. It's unbelievably efficient. Okay, so the first real hero of this story is a network called LeNet 5. It was created way back in 1998 by Jan LeCun, and its job was pretty specific, recognizing handwritten numbers, for reading the amounts on bank checks. It was the first to combine that convolution trick with something called pulling, which is basically a clever way to shrink the image down and keep only the most important bits. And it worked. It was the proof that this whole brain-inspired idea was the real deal. It basically laid the entire foundation for modern deep learning. Now, for a while, CNNs were this cool, promising idea, but kind of niche. Then 2012 happened, and in 2012, everything changed. This was the exact moment that the whole field went from being a quirky academic project to a technology that would literally change the world. This was a start of the deep learning revolution. And this number right here, this is the reason why. At a huge competition in 2012 called ImageNet, a CNN named AlexNet showed up. Now, before this, the best models had an error rate of over 26%. AlexNet, it hit 15%. I mean, that wasn't just a little better, it was a complete earthquake. It absolutely demolished the competition and screamed to the entire world that deep learning was the future. So, what was AlexNet's secret sauce? Well, it was basically this powerful new recipe. You take a really, really deep network, you feed it a gigantic data set, that ImageNet I mentioned, and then, for the first time ever, you throw the insane power of gaming GPUs at it. That combination, deep networks, big data, and powerful hardware, that's what unlocked this whole new level of AI. Seriously, AlexNet was the big bang for deep learning. The years that came right after were just an explosion of new ideas. Suddenly, you had networks designed for all sorts of things, some to be more understandable, some just to be as deep as possible, others to be super efficient. And before you knew it, we had models with hundreds of layers. It was a wild time. But this race to go deeper and deeper created a brand new headache. As people built these massive networks, something weird started happening. Making them deeper actually made them worse. They became incredibly difficult, almost impossible to train properly. And the solution, which came from a model called ResNet, was just beautifully simple. It was this idea called a skip connection. You can think of it like an express lane on a highway. It just lets the information jump past a few layers. And this one little change to the architecture, it suddenly made it possible to train these insanely deep networks, we're talking hundreds of layers deep, without them breaking down. See, ResNet's whole philosophy was about making the network's job easier. Instead of forcing a layer to figure out a whole complicated pattern all by itself, that skip connection meant it only had to learn the tiny little difference, the residual, that was needed. This idea was so simple and so powerful that the ResNet architecture is still the backbone of most AI models you see today. And that pretty much brings us up to today. But the journey is far from over. We've moved way beyond just spotting patterns. Now, it's about a much deeper kind of understanding. And the whole philosophy of how we even build these things, well, that just keeps on evolving. The newest big thing actually moves beyond convolution entirely. We're talking about vision transformers, or VITs. So instead of just looking at little local patches, they use something called attention. Just think about how your own eyes work. You don't see every single detail at once. You focus on what's important, a friend's face in a crowd or the ball during a game. That's what attention lets these models do. And it helps them understand the bigger picture, the global context of an image. This table really sums up the whole incredible story. It all started with that biological inspiration for LeNet. Then it shifted to just pure engineering. How deep can we go with AlexNet? After that, it was all about being smarter and more efficient. That was the era of ResNet. And now we're in this new phase, moving past convolution and into global reasoning with transformers. It's really a full circle kind of journey. And that right there is the legacy. The whole evolution of CNNs wasn't just about better code or faster computers. It was a fundamental shift in what we thought was possible. We taught machines a skill that, for all of history, belonged only to living things: the ability to actually see. So that leaves us with one last, really big question to chew on. For pretty much all of history, we were the only things on this planet that could look at the world and truly understand what we were seeing. But now we've built a partner in that. So now that machines can see, what are they going to show us? Hey, thanks so much for joining me for this explainer. If you enjoyed geeking out on this stuff, make sure you subscribe, because there's plenty more where that came from.